last talk of this chaotic display session on types is going to be given by by Ben Greenman. So he's going to tell us about how to use ideas from the contract world to better understand blame in gradual typing. If we get the display.
Okay, racket. I see it. Okay, good evening. So in this paper, we take a close look at the landscape of languages that let you mix static typing and dynamic typing. We have three main claims. The first is that type soundness is not strong enough to capture important distinctions in this space. The second is that complete monitoring is strong enough. Complete monitoring comes from the world of higher order contracts. When adapted to gradual typing, what you get is if a language satisfies complete monitoring, then you can use types to predict the behavior of your program. Finally, our third claim is that complete monitoring is important even for languages that fail to satisfy the property. The reason being is it gives you a precise way to measure the quality of a blame error. First things first, what do I mean by a mixed typed language? It's simply a language where you can have both typed code and untyped code. So a program is made of different chunks, different modules, if you will, and they can share values when the program runs. We don't need a special dynamic type to get into this situation, so I'm not going to talk about a dynamic type anymore. There are many reasons why you'd want a mixed typed language. One of them is for prototyping. Suppose you have a new idea and you don't want to satisfy the type checker while you're sketching out the first implementation of what you want. Maybe you're building a consensus protocol and you don't want to decide whether to use floating point numbers or integers internally. You can defer that choice and But the key thing is you can rely on types that other people have written. If there's existing typed code that's a library, you can depend on those types. Another reason is for reuse. If you're working in a typed language and one day you find that there's a library that implements some functionality that you wish you had, you can get it immediately because you can mix typed and untyped. So, yes, many reasons. And with all these excellent motivations, it's no wonder that there's a whole cottage industry of adding static types to previously untyped languages. So here's just a few of the many names in this space where we have an old dynamically typed language and a new typed twin on top of it. Huge diversity here. But the diversity comes in two forms. Some of these languages take fundamentally different approaches to how do we do this mixed type interoperation. The other differences are just because JavaScript is a different language from PHP. So how do we separate the important fundamental differences from the surface syntax? Similarly, there are many models in this space that also work towards this idea of mixed typed. Yeah, I got lazier with the slides, so there are fewer names on it. But again, it's a huge landscape. So this is what I'm talking about. People have explored the space of mixing typed and untyped and planted a flag somewhere on it. Our research agenda is identifying points of interest in this landscape. And each point is a semantics for a common surface language, and these can be compared systematically. And the goal is to find formal properties that set up borders between these interesting points that characterize parts of the design space. A definite non-goal is to find property after property and restrict the landscape to a single point. All of these have merits. We're still learning what's the best way to mix typed and untyped, and there are many trade-offs. I mean, theoretical trade-offs and pragmatic trade-offs. So we really want to understand the whole space. Okay, so as a warm-up to what I mean about characterization, let's talk about optional typing, otherwise known as erasure. Suppose I have a function f that says it expects a pair of numbers. And then inside the body of the function, we do something with the first element of that pair. If we're in a mixed type language, we can call f from untyped code. And untyped code can supply any value that it likes, including the integer 9, to this function that expects a pair. In an optionally typed language, the types mean nothing when we run the program. They're erased. So this number 9 goes into the body of the function. If this happens, the best we can possibly hope for is an error when we try to take the first element. We're not guaranteed that an error will occur, but hopefully something happens that says, okay, I expected a pair and that's not what I have because of this elimination form, but not because of the type, because it's been erased. So we have some important consequences. Types are meaningless when we run the program, and therefore they cannot help you to debug the program when you realize it's not running as you intend. So these are important things to be aware of. It would be nice to have a way to diagnose whether or not a language could suffer these symptoms. The diagnosis is type soundness in this case. Languages that fall into this purple block at the top left satisfy a kind of unitype soundness. That means no matter the type of a surface expression, if the expression reduces to a value, all I can say is that it's a well-formed value. I can't say anything about the shape of the value. The type has no predictive power. Now the rest of the space is more or less type sound, but we can say more. There was a wonderful paper last year at ICFP with the same speaker and the same session chair, where we realized we stated there are different notions of type soundness that have arisen in these different implementations of mixed type satisfy different notions of type soundness. Here's the paper in one slide. We looked at free semantics in an apples-to-apples way. The erasure semantics that we just saw, and in there, types predict nothing, and we have unitype soundness. Another approach is transient approach, where types predict the top-level shape of values. And this can be enforced by simple tag checks. Third approach is natural semantics. And here types predict the full behavior of values. And this can be implemented using higher order wrappers. Okay, so we have three ways of running the program that all have practical interest. And the ICFP paper said, they satisfy different type soundnesses: unisound, tag sound, and full type sound. So here's a way of understanding the space. But unfortunately, this boundary between tag sound and type sound is not as firm as we would like. Let's look a little closer. So on the previous slide, we say transient does tag checks, and then you can predict the top-level constructor. Natural uses higher order wrappers, and it lets you predict the full behavior of the value. In this paper, OOPSLA 19, we introduce a semantics that we call amnesic, which uses higher order wrappers to implement first-order tag checks. Because we have higher order wrappers, amnesic satisfies full type soundness. Because we're doing tag checks, well, there's some more to the construction. It has exactly the same behavior as transient. It computes the same values, and it identifies the same errors. Identifies the same programs as errors or not. I want to acknowledge this idea of having higher order wrappers but not using all of them. Has some roots back in Michael Greenberg's POPL 15 paper, and then it was independently discovered, I think, by Castagna and Lavin at ICFP 17. But we're the first to have a semantics that's exactly like transient and has exactly the same type soundness as this other approach. Okay, clearly, type soundness is not enough to separate the space. We want something that looks like this with 4 regions, but we're missing the property at the top right that says, how do we separate this natural fully sound from amnesic fully sound, but not fully checking? Since this has all been pretty abstract, let's do an example. We talked before about prototyping and about library reuse. We're going to combine these two into a single example. I mean, surely if your mixed type language can handle one, it should be able to do both at the same time. We'll have an untyped script connected to an untyped library via a typed API, and we're going to send a higher order value across the boundaries between them. And the application we'll look at is a clickable plot. So we want to plot some data, accept a mouse click later on, and once the mouse is clicked, use a callback that came in from the untyped script to draw a picture. So first, here's the script that our untyped client wrote. At the top of the file, we have our callback h, which is going to go across the boundary. H is expecting a pair of numbers, because the API in the middle says, right. We have the API says you can interact with this thing called the click plot. It has a constructor that accepts a callback, and then when a mouse is clicked, that callback will be used to help draw an image. So this H on the left is waiting for a pair of numbers because it relies on the type in the middle. So when it gets the pair, we check the first element and then return an image. Down below on the left, we create a click plot using the callback, and then later on, we show the plot, and then a click happens. The highlighted type describes the argument to the constructor in the library all the way to the right. And yeah, the thing to notice is that the API promises a pair of numbers to the untyped client. And the client expects a pair of numbers. Okay. Then if we look further into the library side, we see that the API says this mouse handler will receive a mouse event value, and the library sends that mouse event directly to the callback. So we're expecting a pair on one side, and we're sending a mouse event on the other side. This type is incorrect. Whoever wrote the typed API made a mistake and mixed up a pair representing, say, x and y plot coordinates with this mouse event that's actually coming in through the library. So our question is, what happens to the poor client who relied on these types to experiment with a new program, but the types misled the programmer? Or the types have a claim which may or may not be enforced. There. Okay, so with transient and amnesic, the value goes through to the client. And with natural, it stops because the type is checked and it says, mouse event is not a pair of numbers. Now, imagine the chaos if there was an amnesic TypeScript. There would be new graduates getting out of college, taking their soul-crushing software engineering jobs and working in JavaScript. But then they hear, there's this new amnesic, which is fully typed sound. I read about that in TAPL. I want type soundness. So then they start to program, and they know they can mix untyped and typed. So they look at those typed definition files and write new untyped JavaScript. And all of a sudden, type soundness means nothing. The code that they have on the left in the client receives arbitrary JavaScript value, and the types in the middle meant nothing. So this is important. So as we've seen, what's happening is we have three components in our program. And this callback H travels from the untyped component into a typed guy, then from typed to untyped. And since H is a higher order value, this boundary crossing sets up a second direct boundary between the two untyped components. And the question we have is, do types guard the callback channel? And we've seen two different answers to this question. Transient and amnesic say no, types did not guard the callback channel because this is a communication between two untyped components. That's why type soundness has nothing to say about this, because the direct interaction is between untyped code. And natural, the answer is yes, this channel is protected because it came about through a typed API. Enough about implementations. In terms of properties, what this means is that type soundness does not guarantee that the callback channel is protected. Complete monitoring does. So now we have the picture that we want. We have a nice characterization of the space. And we can summarize what we have so far in a table. So natural is the only one of the three that satisfies complete monitoring. And this distinguishes the different behaviors in a way that type soundness does not. You see there's some space in the table. So this is only half the story that we go into in the paper. The second half has to do with blame. Okay, so far with complete monitoring, we're talking about whether or not a check happens to enforce a type. So beyond that question, in either case, whether or not there is a check, eventually some programs will have runtime type errors. The goal of blame is to help a programmer trace back from this error what could have gone wrong in my program. Let's look at our plot example with the natural semantics that checks all the types. The ideal error that we would like to see Okay, we see an error right at this boundary between API and client. It says, I expected a pair, I got something different. And it explicitly names. We're blaming the library, which supplied the value, assuming that these API types are correct. So the programmer sees that there are two parties involved with this, and something went wrong at the boundary, so either the type is incorrect or the behavior is incorrect. But I know exactly where to start looking to get my program to work as I want. Now let's go to the transient and amnesic side. The best we can hope for over here is an error. Again, the error might not occur, but supposing we get an error. And then if we get such an error, we'd like to see two boundaries involved. Because that value, which came from the library, has crossed two boundaries, first to the API and then to the client. The important difference here is in natural, there's going to be at most one boundary to blame for such errors. But in a system that doesn't satisfy complete monitoring, there could be any number of boundaries that the value has gone across before it reached a place that errored. So because this is the state of things, there are two things that we care about. If there's a set of potentially responsible parties, first question is, if we blame some parties, did we blame only responsible parties and nothing irrelevant? A second question is, did we get all of the responsible parties? So, of course, these are soundness and completeness properties, and the goal is to be both blame sound and blame complete, which means you've gotten exactly the parties that are responsible and then no more. So we attempted to prove blame soundness and completeness for both, for all three. Complete monitoring gives you blame soundness and completeness. It's right there. You've checked all the channels, so the channel where an error occurs is exactly the one that you want to blame. Transient, which implements its checks without any higher order wrappers, satisfies neither soundness nor completeness. Now, this is not the end of the story for Transient. There's more details in the paper, but for the talk, I'll come to it in the questions. Amnesic uses wrappers, and with this, we can implement the blame algorithm that satisfies both of these properties. So Amnesic can find exactly the guilty parties because it has higher order wrappers. But without wrappers, it seems like a challenge to get these. I just have one more slide, so we're doing fine. Okay, there's the table of results again. Now, in closing, I want to leave you with one thought. We normally talk about gradual typing in the context of new languages or existing dynamically typed languages that we want to add types to. We don't normally think about it in the context of a language like ML or Haskell. But every useful typed language depends on untyped libraries. Either it's the runtime system or something deeper down that we want to reuse and interact with. And when we prove type soundness for one of these typed languages, we trust the untyped code. It sits outside of the model. So it's typed sound, assuming that all this untyped code and all this FFI code is correct. With gradual typing, we make these trust boundaries visible. And in doing so, it challenges our baked-in notions of types and what they mean. So my message today is that there's more to types than type soundness. And in particular, there's complete monitoring. It lets you use types to reason about systems that compose typed and untyped code. And furthermore, even for languages that fail complete monitoring, it lets us precisely talk about blame errors. Thank you.
Thank you, Ben. Questions? Please come to the front.
Okay, so you might be wondering why Transient fails both properties, blame soundness and blame completeness.
Okay, maybe.
I'm glad you asked. So actually, let me tell you the way that it fails soundness and completeness, because that's much easier to say shortly. It fails soundness because suppose you have a function that you export to two different clients. One client uses the function and all goes well. Another client uses the function and encounters a type mismatch. Transient will blame both of these clients. So that's unsound because one of them is not relevant to the problem. And it's incomplete because Transient does not touch untyped code. So if an elimination form happens in the untyped part of the program, and that elimination form is a boundary crossing, it'll be missed in the completeness part. So, I mean, there's an easy way to recover soundness by reporting no boundaries, and recover completeness by reporting everything in the source code. But the question is, how close can we get to both?
Any other question? So actually, I was wondering, so you show us how to refine a bit the space thanks to this notion of complete monitoring. Do you believe that this is the end of the characterization of the space? Are there some other areas of the map that are worth capturing precisely with other properties?
I have no secrets to share. I mean, no.
Confidential.
I mean, at the time I thought this characterization by type soundness was a very nice one. So it's been a surprise in the past year that it's definitely not enough. So, I mean, we'll just have to see where the research goes.
Okay. And so there was this empirical study on how people, what semantics people were using, and at the time amnesic didn't exist.
Yeah, that's correct.
So what do you have any intuition of?
There's an empirical study in DLS 2018, the behavior of gradual types, and it compares erasure, transient, and natural in a mystery languages style approach. So you see one source code program and 3 ways of running the program. And the question is, do you like and expect? Like and or expect. You have to answer on 2 dimensions at the same time, this behavior. And the results we saw in that survey were people preferred checking all the types all the time. So they preferred this top right corner. The survey didn't ask about performance. It didn't ask about how hard the system would be to implement or whether it would be compatible with an old language. So, but, you know, with those things off the table, the preference was for check all the types.
And what's your hypothesis with respect to amnesic, if amnesic would have been there?
Oh, no, I think amnesic wouldn't. It's the same as transient. So yeah. People would say, no, I prefer the top right. There's one more thing I want to say about transient. Transient, okay. The whole left side of the table is relative to a model of what party is responsible for what values that flow through the program. This model is a standard model from the contract literature, and it reflects an algebraic intuition about how values flow through the program. But if you adopt a different model and say that values also go through a heap as they travel through the program, then we can show that transient is blame sound. The question is this going to be a useful model for programmers? And it's too early to say.
Okay. No questions? Yes, one? Can you? No, okay. So, James?
Since Jan's left, I can ask this. How would Jan's concrete semantics fit into the landscape?
Oh, concrete is off the map. Because in concrete semantics, every value comes with a type. There's no such thing as an untyped value. This makes a lot of sense in the object-oriented setting, because every value is an instance of a class. And if a class is a type, then it's natural that every value has a type. But that's not the landscape that we're looking at. Thank you very much for the question.
Okay, no more questions? Okay, so let's thank Ben again. And that's the end of the session.